Homework last night was page 601. We're going to look at 5, 7, and 8 from page 601, starting with number 5. It says a positively charged lithium ion is traveling horizontally along the Earth's surface. Describe the deflection due to the magnetic force if the ion travels in these 3 different directions. All right, first of all, it tells me that lithium is positively charged. That's good, because unless you're doing chemistry, you might not know that a lithium ion is a positively charged ion. Okay, the good news is they don't require us in Physics 30 to know any chemistry. So if you ever have a question with a lithium ion or whatever other ion on a diploma exam, and you may, we know how to deal with charged particles. We know how to deal with ions. We just don't know necessarily what each ion is, positive or negative. They'll always tell us. So a positively charged lithium ion. Right away we see that positively charged and we're thinking, okay, this is going to be a hand rule, right? It's going to be a right hand rule because it's a positive particle. Now, which hand rule is it? Is it the wire grasp rule? Is it the hand rule, the coil rule? Or is it the hand rule for deflection? Which hand rule is it? We get a charged particle. It's not an electron, it's not a proton, but it's still a charged particle. And it's traveling perpendicular to a magnetic field. Look, it's traveling horizontally along the Earth's surface in a magnetic field, in the Earth's magnetic field. We want to find the direction of the force. This is clearly a hand rule for deflection, right? So let's do that. Let's take our right hand out. Everybody take your right hand out, even if you got these. Let's stick our thumb from south to north. Now, what do they mean from south to north there? I think they mean geography. Like when they say south to north, I think they mean that way towards the Arctic. Okay. They should really say, though, whether they mean geographic north or whether they mean magnetic north. Okay, we're going to assume geographic north here, unless they say otherwise. It means we're going to stick our right thumb towards Calgary or towards the Arctic. My fingers are going to go in the direction of the magnetic. Oh, wait a second. Wait a second. The particle's going this way. The magnetic field is also this way. What do we know about that force? What's the value of the force? Jack? 0. There is no force there. So this isn't perpendicular, actually. That's okay. We know how to deal with it when it's parallel, too. It's even easier, actually, when it's parallel, right? East to west. All right. We know the magnetic field still goes that way towards the Arctic. But now the particle's traveling towards the west. Okay, so I'm going to stick my thumb towards the west, towards the mountains there. Fingers towards the Arctic. Palm points which way? Don't say down the page or anything like that, right? Because this is down. When our frame of reference is the Earth, it's up or down, not up or down the page. So the palm points downwards.
Why is the magnetic field south?
Magnetic field always points toward magnetic south. Always points away from magnetic north toward magnetic south.
Magnetic south to north? Like
Yeah.
geography?
Yep. Yeah, and then that's that way, right? Yeah, if you turn around and picture you're driving to Calgary, we say it's going north, technically it's magnetic south, so the magnetic field goes that way. But I'll tell you what, Kyle, you bring up a kind of a good point, right? You're kind of in a room right here, kind of in an isolated room, and we look out the window and maybe we see the mountains and we know which way is west. Maybe we don't. Maybe it's diploma exam day and you're in the cafeteria and you can't see anything because there's no windows. You don't know which way is north and which way is east and south and west. I'll tell you what, you're going to be in the cafeteria, guys. The stage is north. Okay, the stage is north. When you're in the cafeteria, you're going to be facing the other way. The stage is north. But you don't really need to know that because in the end, you can pretend any way you want is north as long as your east, south, and west are relative to that. So let's pretend, Kai, that we're in a room that we've never been in before and we're not sure which way is north, south, east, west. Let's pretend that way is north. Okay, if that's north, then that's going to be south, and that's going to be west, and that's going to be east, right? Okay, when you're looking north, west is to your left, east is to your right. Okay, but if that makes you uncomfortable to kind of make it up, it works. But if it makes you uncomfortable, then you can always remember, since your diploma exam is in the cafeteria, the stage is geographic north, magnetic south. Okay, The magnetic field points toward the stage. The Earth's magnetic field points toward the stage. What about upward into the atmosphere? Okay, the charged particle going upwards into the atmosphere. Fingers go towards magnetic south, towards the Arctic this way. Okay, palm points toward the, we don't want to say toward the right, we want to say toward the west, toward the west, yeah. It's okay, by the way, when you get into a diploma exam, to do something like this. It's okay to make whatever notes you want. But if you're going to get west and east mixed up, you might want to make a little note here to remind yourself that it's not magnetic north, though. Maybe you want to even say this. The Earth's magnetic field points this way to remind yourself that it points toward the north. Okay, whatever, as long as you don't take that information into the exam with you. It's okay to do that. All right, next question was number 7. Number 7 says a 0.020 gram metal ball with a charge of minus 3 microcoulombs is thrown horizontally along the Earth's equator. How fast must the ball be thrown so that it maintains the same height above the Earth's surface if the magnetic field caused by the Earth is 5 times 10 to the minus 5 Tesla? We've done something like this before, haven't we? Do you guys remember what the concept is here? Clearly magnetic force, right? But if it's maintaining the same height above the Earth's surface, what is it that we're going to want to do here? What condition must be met if it doesn't fall because of gravity? I mean, everything wants to fall because of gravity, right, Nathan? The net force equals 0. So if the net force equals 0, the downward force has to balance the upward force. We're going to say the magnetic force, which must be the upward force, equals the gravitational force, the downward force. Now, get out the red pen, because there's some stuff to circle here. We've got 0.02 grams. We've got microcoulombs. We've got the fact that it's a negative charge. Okay, all these things that are kind of different than what we're used to seeing. The magnetic force on the charged particle is QVB. The force of gravity is m times g. We're looking for, what are we looking for? V becomes m times g over q times b. 0.020, what am I doing here? Yeah. I'm converting to kilograms, and lots of people like to move the decimal place over. I'm not a fan of that. Okay, if that works for you, that's great. But for me, it's easier just to tack on a 10 to the minus 3 on the end of that, and then I don't have to worry about moving the decimal place over the wrong number of spaces. Right? Is it 0.0002 or 0.00002? Or right? Easy to mess that up, for me at least, easy to mess that up. So I find it easier just to tack on a 10 to the minus 3 on the end of that. Multiply it by 9.81. Q is, what is Q? Minus 8, minus 3. Is that a 3? Yeah. We're going to drop the negative sign, though. 3 times 10 to the minus 6 coulombs. Magnetic field strength is 5 times 10 to the minus 5 Tesla. And what do we get for the speed there? 1.3 times 10 to the 6th. Thank you, Sasha. Meters per second. That's a pretty typical speed, by the way, for a charged particle. 10 to the 4, 10 to the 5, 10 to the 6 meters per second. You get something outside that range, it doesn't mean you're wrong, but I get 10 to the 6, and right away I'm thinking, okay, I'm right. Okay, I'm pretty confident when I get that answer. Now, if you got 1.3 times 10 to the 9, you're wrong, because it can't be bigger than 3 times 10 to the 8. Okay, but this is pretty realistic. Finally, let's take a look at number 8. It says an alpha particle with a charge of 2 times the elementary charge is traveling perpendicular through a magnetic field. What's the minimum gravitational force required to suspend the alpha particle at the same position above the Earth's surface? This is the same thing, isn't it? Right? Suspending it above the surface. What are we saying there? It's not going up or down. If it's not going up or down, then forces have to balance, just like they did in the last one. The only force we have here, the only 2 forces we have are the magnetic force and the gravitational force. Why can we not set it equal to the centripetal force here? Okay, if we remember things and we don't think about things, then there's a good chance somebody's going to do that, right? Oh, hey, I remember doing magnetic field problems. I remember that I set Fm equal to Fc. That's what I'm going to do here. Why can I not do that here? There's a pretty simple reason why we can't do it. Pretty simple reason that you're going to miss if you're not thinking about it. But a pretty simple reason that if you do think about it, then you should be able to nail here. Why can we not use Fm is equal to Fc? Because it isn't going in a circle. It's maintaining the same height above the Earth's surface. So it's going in a straight line, right? Can't say Fc if it's not going in a circle. Don't ever blindly do that. When we're solving a problem and writing down an equation, know why you're writing it down. Know why you're writing it down. I say all the time, try things, try different things, but know why you're trying something. Okay, don't just blindly try something. Okay, I'm going to try this because I know that the upward force must balance the downward force if it's maintained in the same position. Before I do that, I should have actually circled this, the fact that it's an alpha particle, right? Because positive particle, right hand if we have to do a hand rule. Oh, wait. We don't need to plug in mg, do we? Let's just say QVB is equal to FG. Is that okay? If Fm is equal to Fg, then QVB is also equal to the force of gravity. Okay, we got the charge, 3.2 times 10 to the minus 19, and we got the speed, which 1.02 times 10 to the minus 5, which is an unusually low speed for a charged particle, but happens. And what do we get when we multiply those together? I don't know if that's right or not, but it seems good because we would expect to get a force of gravity that's really small on a particle that's so small, right? All right, I want to work on two quick multiple choice questions, and then we're going to do a little bit of new work here to finish off the day here. The multiple choice questions go with the information here that you will not recognize in the slightest. That's okay. Okay, we can deal with context that we've never seen before. The two questions that I want you to do are number 77 and 78, please. Okay, we're going to have a look at these two questions now. You read through this photon-matter interaction. Lots of you have never even heard of the word photon, unless you're a Star Trek fan and you've heard of this photon torpedo thing, which is really like a flashlight. Because a photon is just a little particle of light. Fancy name for a flashlight. Next time you need a flashlight, ask your mom, where's the photon torpedo? See if she knows what you're talking about. When a photon passes through matter, it interacts with the atoms and their electrons. There are four important interactions with matter that a photon can undergo. In the end, guys, you don't know any of these interactions at this point, and that's okay. That's okay. It doesn't affect whatsoever your ability to solve this problem. Yeah, I'm going to skip forward past those interactions because you've read them and because it doesn't really matter for us when we're answering this question. We look down here. We get this photon, it collides with this atomic nucleus, and then look, this positron, we never heard of that before, but it's positive. This positive positron gets deflected this way, and this negative electron gets deflected downwards this way. What's the question going to ask us here? We need a magnetic field to cause these paths. So basically, we're looking at a magnetic field that's got to be perpendicular to the motion of the particle. The particle was moving to the right, so that means the magnetic field is either going to be up, down the page, it's going to be into the page, or it's going to be out of the page. Because the particle is deflecting upwards and downwards, this isn't going to be it. Okay, it's either going to be into the page or out of the page, because in the end, we know that the particle has to be moving perpendicular to the field, but we know that the deflection will also be perpendicular to the field. So it's going to be into the page or out of the page. What you got to do at this point is pick a particle. Pick the positive, pick the negative, it doesn't matter. I'm going to pick the negative, and I'm going to say hand rule for deflection, because there's a magnetic force on this, right? It's not a wire grass spool, it's a hand rule for deflection because of the magnetic force. Thumb to the right, palm points downward because the electron is deflected downward. Fingers go into the page. So the answer for the magnetic field would be into the page. Now, what if you had to pick the positron? this mysterious whatever a positron is. Okay, right hand, thumb in the direction of the particle, which is initially to the right. Palm points upwards because the positron is deflected upwards. Fingers go into the page. So any way you look at it, the magnetic field there is into the page. In 78, during pair production, the speed of the electron or of the positron can be calculated by measuring the radius of the path. What's an equation that describes the speed? Well, how do we analyze a charged particle in a magnetic field when we're involving the radius of the path? How about Fc equals Fm? We'll say mv squared over r equals qvb. Solve for v here. Q times b, the r goes up by multiplying, over m. So the answer is going to be A, bqr over m. Good? Okay, we're going to do this last little bit pretty quickly here, guys. This is new, but it's not crazy hard. The first part of it might seem a little bit out of place. We did electricity in our last unit. In this unit, we're doing magnetism, but yet I'm defining electric current force. The reason we're defining it here is because our last unit involved static electricity, which is the buildup of charge, not current electricity, the flow of electric charge. In addition to that, we do electric current not because it's important in itself for us in Physics 30, but rather because it's important in doing the next magnetism topic. So we kind of do it along with that topic. Electric current is the rate of flow of electric charge. It's not the speed of the charges. It's the rate of flow of the electric charges. In other words, it's how much charge is flowing by a certain spot per second. It's analogous to this. Okay, you're a police officer standing on the side of the highway. Okay. Somebody else, your friend, is doing a traffic study, counting the number of cars. So what are you doing? You've got a radar gun trying to test the car's speed to see if they're speeding. Your friend is counting the number of cars that are going by so that they can figure out how many cars go by in a day or whatever. When you've got your radar gun out there, you're measuring the speed of the cars. That's not analogous to current. Your friend who's looking at his or her stopwatch and counting, oh, there's 1, 2, 3, 4, 5. 5 cars just went by in 1 second. That's analogous to current. The amount of charge per second that flows by. The amount of cars per second that flows by. Not how fast they're moving, but rather how much of it flows by per second. That's electric current. Now, the symbol for electric current is a capital I. And of course, since it's a measure of the rate of flow of charge, it's going to be charge over time. Charge is going to be measured in coulombs. Time is going to be measured in amps. The units that we could use for charge over, coulombs and seconds, I should say. The units that we're going to use for current would be coulombs per second, right? Charge over time. But we introduce another unit now that means the same thing as a coulomb per second, and that's going to be an ampere. Okay, this is what you saw in your quiz yesterday, right? That I said, hey, can't be the answer, you haven't seen it yet. Now you've seen it. 1.0 coulomb per second is equal to 1.0 amp. Ampere, sometimes we abbreviate it as an amp. We're going to do a really quick example, but I'm not going to give any problems to work on with this because I think it is pretty straightforward for us. We'll go straight to the topic that we really want to cover today, and we'll do an example with that one with a couple problems right after we're done this. It says calculate the current in a wire through which 20 coulombs of charge passes in 4 seconds. Okay, this is our charge, this is our time, and we want to find the current, capital I. So we're going to say I is equal to Q over T, which is 20 coulombs divided by 4 seconds. Easy enough, right? 5.00, what are the units? We could say coulombs per second, or we could say 5.0 amps or amperes. Now, why have we just done that? Why have we just learned about electric current? Because we want to look now at electric currents in wires that are exposed to external magnetic fields. We've looked at charged particles just moving through the air in external magnetic fields. They experience a force, right? And that force is equal to QVB. In the end, it ends up going in a circle, so that force can also be equal to mv squared over r. Now we want to look at the specific case of charged particles in a magnetic field, but moving through the wire exposed to the magnetic field. Well, they're going to experience a force just like the charged particles that are moving through the air experience a force. In fact, the force on each of those particles within the wire is still QVB. But because these charged particles are all moving within the wire, and because they all experience a force, and because they're in the wire, they can't go in a circle, right? Like the charged particles in the air could go in a circle. These guys can't. Because they're all on the wire, because they all experience a force, because they can't go in a circle, when they experience the force, they drag the wire with it. So the wire also experiences a force. The charged particles individually experience a force equal to QVB. The wire itself also experiences a force, but it's not equal to QVB. That force is equal to ILB. Now, what do these variables mean? Of course, Fm is magnetic force, is measured in newtons. I is the current, the electric current that we just learned how to find. Okay, it's Q over T, measured in amps. L, sometimes I write that myself as a capital L. They always write it on the data sheet as a lowercase l. I sometimes make it a capital L so as to not mix it up with a 1. Okay, when it's written in typewriter, type font here by a computer, then you can distinguish an L from a 1. When I handwrite it, you can't distinguish an L from a 1. So let's make it a capital L when you're writing it by hand. That's the length of the wire that's exposed to the magnetic field. Not the entire length of the wire. If you have a 5-meter long wire, but 3 centimeters is exposed to the field and the rest of it isn't, then the length is not 5 meters, the length is 3 centimeters. It's the part that's exposed to the magnetic field. And of course, B is the magnetic field strength. And it's measured in Tesla. What does that little upside down T beside the L mean? We know this, right? Yeah, the wire has to be perpendicular to the field. Why? Well, because the charged particles are moving through the wire. So if in our the last thing that we did, the charged particles have to be moving perpendicular to the field, well, they do here too. The only way to accomplish that is to have the wire itself perpendicular to the field. How do we find the direction of the force? Just wait patiently for a sec here, guys. How do we find the direction of the force? No. Yes, it's the hand rule for deflection. It's the exact same rule that you use for the charged particle in the field. Look, if a charged particle is going through the air and the force is downward toward the ground, and the wire is pointing that way and the electrons are moving through the wire that way, then the force on the wire is going to be in the same direction. So you're doing the exact same rule that you've already done, the hand rule for deflection. This time it's thumb in the direction of the current, which is the direction of motion of the particles. The question says, 12.4 says, an 8.5 centimeter length of wire, centimeters in red here, lies perpendicular to an external magnetic field of 4.20 millitesla. Look, it's perpendicular. That means any equations that we've learned here are valid. If it's parallel, what would the force be? 0, same as it was on charged particles moving through the air. Here's the current. We want to find the magnitude and the direction of the magnetic force. The magnitude is going to be ILB, which is 2.10 times 0.085 times 4.2 times 10 to the minus 3, which gives us 7.50 times 10 to the minus 4 newtons. What's the direction of the force? Hey, left hand, thumb in the direction of the particle, which is into the page, right? Because that's which way the current goes. Fingers go from north to south in the direction of the external field. Palm points which way? Toward the top of the page, up the page, or toward the top of the page. Don't just say up the page or toward the top of the page. Your homework for tonight, all you got is 2 questions to go with that on page 605, guys. Okay?